In this video, we are going to explore an interesting phenomenon in electronics: the varying resistance of an LED as we change the voltage applied to it. LEDs, or light emitting diodes, are widely used in various electronic applications, but there's more to them than just them lighting up. We're going to dive into the relationship between voltage, current, and resistance in an LED, and we'll be using this example that I have on screen. Just a quick overview of LEDs. An LED is a semiconductor device. It emits light when electrical current passes through it. Unlike the resistor that I have on the top of the screen, an LED does not have a constant resistance. Instead, its resistance changes based on the voltage applied across it and the current flowing through it. In a typical LED circuit, we apply a small amount of voltage. In our example, we'll be applying 12 volts. The LED might not light up all the way because the voltage is not enough to overcome the threshold. In our practical example, we'll be varying the voltage and seeing how that will affect the illumination of the LED. At the top of the screen, I have a 1000 ohm resistor, or 1K ohm resistor. I'm going to take my multimeter here on the right, and I'm going to measure the resistance of that resistor. We can see that the value on our multimeter is roughly 1000 ohms. Now I'm going to take the multimeter and measure the resistance of this LED. We'll see that the resistance is somewhere around 8 million ohms, 8 mega ohms. In order to understand our next measurements, we need to see what the voltage is when our multimeter is reading resistance. So I've set my right meter to read resistance, and I'm going to connect my left meter reading the voltage. So this is the output voltage of my right meter. So when the meter is reading the resistance of a circuit, the output voltage of that meter is approximately 2.77 volts. Okay, with that information, we can disconnect the meters. I'm going to connect the left meter to a power supply. It's just an external power source that we're going to provide to the resistor and the LED separately. So the left meter is reading 1 volt from the power supply. And then I'm going to set up this right meter to read the current of the circuit. So this will be set on milliamps DC, and I'll provide 1 volt to one side of the 1000 ohm resistor, and the other side I will connect this ammeter in series. So we can see now the value at 1 volt there is 1 milliamp of current flowing through the circuit. As I increase the voltage on the left at the power supply at 2 volts, I have approximately 2 milliamps. At 3 volts, I have approximately 3 milliamps. At 4 volts, I have approximately 4 milliamps. So I'll continue to increase the voltage on the left meter, and we'll start to see that there is a direct relationship between the voltage on the left and the amperage on the right. This type of behavior is described as being linear, meaning that as we increase the voltage, proportionally we will increase the amperage in a circuit that has a fixed resistor. If we take one of those values, in this example we'll do 6 volts, and we divide it by the current, 0.006 amps. It was 6 milliamps in our measurement, but that converts over to 0.006 amps. It gives us a value of 1000 ohms. If we were to do this same calculation for the rest of the voltages and currents, we would get this fixed value of 1000 ohms, which is what we would expect when we have made a measurement of a 1000 ohm resistor. We're now going to switch our current measurement to the LED. I'm going to leave the left meter connected to the power supply. So now we're just passing our current through our right meter, and we're going to read that. This current is going to be so low that I'm going to switch to microamps initially as we make these measurements. Notice at 1 volt we have 0 microamps passing through the circuit. We move our way up to 1.5 volts and still no current that we can read on our meter is passing through the LED. At 2 volts we still aren't showing any current passing through the LED, at least the meter's not reading it. So right around 2.3, 2.4 we start to see current moving through the circuit. It's a fairly small amount, about 40 microamps right now. At 2.8 volts, around there, we actually start to see the illumination of the LED. And then now all the way up to 5 volts, we're seeing about 1,000-ish microamps on the right meter. So I'm going to switch back to milliamps, and we can see that kind of relationship that's occurring. So at 6 volts, we're about 2 milliamps, and we'll continue to move forward. This specific LED is rated at 12 volts, so at 12 volts this is supposed to illuminate. A lot of LEDs, if it's just a raw LED by itself, are even to start to see illumination around 2.3 volts. So all the way at its operating area around 12 volts, we have approximately 4.5 milliamps of current passing through it. Let's perform a calculation to find out the resistance at 2.7 volts. We divide that by 0.00012 amps. That gives us a resistance value of 22,500 ohms. If we do that same calculation on other voltages, we'll see that the resistance varies based on the voltage that is applied. So it does not follow the same thing that we saw on the fixed resistor, where the resistance remained the same regardless of the voltage applied. I pulled this data sheet off of DigiKey's website. A data sheet is simply just describes electrically what's happening with the component that could be found on the site. So this is from a manufacturer called Kingbright, and they publish this information so that you can know how to mount their product on your PC printed circuit board and know the electrical properties. But the thing that we care about, this is a 3-color LED. It has blue, reddish, orange, and green. And if we come down here, we're looking for the data on the forward voltage of the LED. So this specific graph is an indication of the blue LED's forward voltage. So we see right here that not until we reach 2.7 volts do we start to see an increase in current. So the current is not increasing linearly. We see this current changes as voltage is applied to it. So that's in direct reference to the resistance. So the resistance is going down as we increase in voltage, and so we see that current flowing. You can see here on the reddish orange one we have a lot less voltage, 1.7, 1.65, somewhere around there, where we start to see the current to flow through the circuit. And we see once again kind of a steady increase that's not linear. And then finally the green one has this published data as well. So you can see most manufacturers of LEDs are going to provide this information talking about the actual forward voltage, and it's going to vary. It's not all the same, but most of them are going to increase in a pattern that's pretty similar to this these 3 graphs that we just demonstrated. Alright, as we wrap up this video, I wanted to re-emphasize some of the key points that we've learned. We first discussed what an LED is. It's a semiconductor device that emits light when current flows through it. We mentioned the property of an LED known as the forward voltage. So the forward voltage is the minimum voltage required for the LED to start conducting and emitting light. Most of the time that value is somewhere between the ranges of 2 to 3 volts. It's going to vary by manufacturer, and even within the same manufacturers of the LED, that property might change depending on the color of the LED. Then finally we talked about measuring the resistance of an LED. The problem with that is an LED's resistance is not constant. It changes based on the voltage that is applied to it. As the voltage increases, the LED's resistance decreases, which in fact then allows more current to flow through. And then as more current flows through, we see brighter LED. When we're diagnosing a faulty LED circuit, we want to utilize a voltage drop test instead of measuring just the resistance of the components. I have another video that talks about voltage drop tests that you should have already seen before this. So as you continue to work through the lab exercises on the MMTS, always keep in mind the unique properties of LEDs and use the appropriate diagnostic techniques. Understanding how LEDs behave under different conditions will be crucial for accurate troubleshooting and effective circuit analysis.